All right, so we're ready to get started. Today we're going to continue talking about diffusion models, but we're going to see how we can use diffusion models to model discrete data, and in particular text. And we have a guest lecture by Aaron, who is a PhD student in my lab, and he did some groundbreaking work in this space of using diffusion models for discrete data and language. And so, yeah, take it away, Aaron.
Thanks, Stefano, for the introduction. And yeah, glad to get started. Let's get started. Yeah. To start, I'd like to talk a bit about the general framing of our generative model problem and how things work generally. So typically, we're given a data set, x1 to xn, which we assume is sampled ID from some data distribution p data. Our goal is to fit a parameterized model p theta, often parameterized by a neural network, that approximates our ground truth data distribution p data. And assuming we can learn our p theta well enough, we can generate new samples, maybe new interesting samples would be the interesting part, using our parameterized p theta. And now, if we can do everything together, everything works out, we profit. But there's kind of a bit of math that goes in between, as you all know. So in this class, you guys have learned a lot about different generative modeling paradigms, such as GANs, VAEs, and diffusion models. And the thing that you'll notice for all of these different models, or most of these models that you've learned, is that whenever they draw a schematic diagram about what you should be doing, they normally have a picture. They normally use an image as your most common data modality. So here we have a picture of a dog, a picture of a number, and a picture of a smaller, cuter dog. And this type of coincidence actually isn't, it's not just a coincidence. There's actually a very fundamental reason why we do this. And the reason why is because all of our different all of these different generative models, they're building in the fact that we're working over a continuous data space. So here our data space X is equal to some RD, where you can think of R as each pixel value and D as a total number of pixels, so the values of the pixels. And if we visualize this using some spectrum, as follows, then what's nice is that we can sample points here, here, or there. And these three different samples are all valid images, so to speak. And this is a fundamental property of continuous spaces and the fact that we can interpolate. Now, what I and a lot of other people are interested in, which is a bit converse to this type of setup, is a discrete data space as follows. So instead of having x equals rd, we have x is equal to 1 to n to the power of d, where n is the total number of or is a vocabulary size, so to speak, and d is a number of dimensions. We replace our data points with data points x, where x is just a sequence of tokens, x1 to xd. And then, if we have the setup, we can visualize it with another diagram. This is a lattice, which is the simplest version of a discrete space. And while it's true we can generate samples here and here, which are valid discrete data point samples, we can't really generate samples here or there. We can't generate samples in between or outside of the values because that just doesn't make any sense for discrete data distribution. And as such, this makes discrete data fundamentally a harder problem, as we'll see. And so now you might be asking yourself the question, OK, Aaron, we've learned about GANs, diffusion models, VAEs. These all work pretty nice. Why do we have to go to a completely different regime? Why do we have to go to discrete data? And why does this matter? And I would be remiss if I didn't mention our good friends at OpenAI, who have released these big large language models like ChatGPT, which have really transformed the world in the last couple of years. Also, I would be remiss if I didn't mention other competitors. But yeah, fundamentally, we have this new novel paradigm of large language modeling, which is perhaps arguably the largest advancement in computer science machine learning in the last couple of years. And what's interesting about this data domain is that sentences are fundamentally discrete. So for sentences, it's a sequence of discrete tokens or discrete words that we build up. So as such, it would make the most sense to have a probabilistic model that can generate discrete data like sentences as such. And in particular, if you are familiar with the LLM, large language, natural language processing in general, you may have heard of something called language model pre-training. This is kind of the core step for many of these models where you like learn like a distribution over all of your input sentences. And really what they mean by language model pre-training is you're just fitting a discrete probabilistic model to your internet scale data. So we can see that like this idea is pretty fundamental here. And other applications include stuff in like natural like biology and natural like sciences and more broadly. We have data modalities such as DNA, molecules, and proteins. And all of these different data modalities are fundamentally discrete. And it would make the most sense to try to generate like new novel DNA sequences, novel molecules, and novel proteins, which can have a big impact in our day-to-day lives. And this all requires a discrete generative model. And finally, and this is a bit kind of counterintuitive, we also see a return to discreteness for stuff like images. So this is the schematic for a VQ-VAE backbone. A VQ-VAE or VQ-GAN is one of the many building blocks in systems like Stable Diffusion. And in the middle, we have like this discretized representation, this discretized latent space vectors. And more recent work, and this is like extremely recent, like in the last couple of months out of Google and CMU, has shown that if you just like throw away any continuous notion of your discrete latent space, you only have the discrete component, this actually leads to a broader improvement in results. And results like these tend to show that maybe in the future it's possible to reconcile like images into this broadly discrete paradigm as well. But yeah, so now we know like why discrete data is important. So let's ask the question, why is it so hard? And you might say something like, hey, Aaron, this is all very interesting. Why can't we just adapt an existing continuous space model, like a flow or a GAN? Why can't we just take that and just adapt it to like the discrete case? And well, we have something like this. So we have this diagram. We take some random noise. We push it through some F theta neural network, and it generates an image. And this is like good like way to do our sampling and whatnot. And the intuitive idea here would be like, why can't we just parameterize this F theta to output only discrete values? And since it only outputs discrete values, then we can generate something like text. And we can go through like some examples here, but let's say for flows, we have this kind of correlate. We have this like coupling where we take noise to data, data to noise through our F theta or an F theta inverse that you guys have seen. And the way that this works is that you can like stretch and pull your space. And this allows you to to model a complex data distribution with a simple base distribution and a change of variables formula as such. Now, if we replace all of this type of stuff with like discrete data, so let's say we go from like a discrete random sequence to like we map it like bijectively to another like real sequence that we want to model. Well, do we have a change of variables? Well, we don't really have a change of variables. In fact, the best that we can get is like this type of like setup where our x has the same probability as like this other x. And because of this, your base distribution has to be as expressive as your data distribution, which is why this type of setup like struggles really hard. And for this question, yeah, we have this flow. It doesn't really generalize. Also, we have, let's say, GANs. Okay, we take a noise, we map it to an image, we have a discriminator. And then the idea here is we can backpropagate gradients to update our F theta from our discriminator. And if we replace like the components with discrete values, so we parameterize it to only allow for discrete outputs, then this gradients don't really backpropagate through a discrete value input. And the reason why this doesn't work is because we don't have calculus. So from these two examples, we can broadly see that we'll get through this slide quickly, but our conclusion is that our models are currently too reliant on calculus and it's hard to extend it. So for transformers, this is kind of a modeling question, not like, it's kind of an architectural problem, not a modeling problem, if that makes sense. So kind of for transformers, when you map it like the input like sequence to like a discrete or to like a continuous value, like really the reason why this works and the reason why like people do it is because it like takes your 50,000 or whatever like token space down to like 700, which is much more amenable for computation. But you don't really have to do this. So this is kind of like an architectural decision and has nothing to do with like the modeling, fundamental modeling component or probabilistic modeling part. Okay, why can't we just embed the tokens into continuous space and do this type of like, we embed the tokens in continuous space and then when we just generate the values and we discretize kind of. And actually this is kind of people actually do this for some things. Like in particular, we can take a look at something like images, right? For images, in images, we don't actually store like the whole continuous values of an image because that would be impossible in a computer. We only have finite bit precision. Generally speaking, we discretize it up to like 0 to 255. We have this discretized representation. This is what we store as our quote unquote like ground truth image. And the idea here is that for our like generative modeling, what people do use for like a system like Stable Diffusion or any generative model broadly is a two-step procedure. First, you have your continuous generative model. You generate a continuous image, and then you discretize it to like the nearest like value, and this becomes your discrete image, which is kind of like what people do generally speaking. So this is how they kind of get around the discrete nature of images and use continuous models here. And the reason why this works for images in particular is because like if we have the image's values 0 to 255, this is a typical range for an image pixel value, then we can just embed this into like some continuous space like directly. So we just embed it on the real number line. And if we generate like one of these three different like generations, well, what we can do is that we can just easily discretize because we just round to the nearest number. This is very simple. Now, if we have something like tokens, let's say for a natural language, okay, like there's no way we embed this into a continuous number line like that. And generally, like the way that people do this is like something very high dimensional. Like this is 2 dimensions. People generally do like much higher dimensions than this when we try to do our embeddings. And if we try to like generate stuff here and try to generate and discretize something here, what you're going to end up with is like, okay, yes, sometimes your generations will be good. Okay, so if we had generated tokens like in the green X marks there, it's all good. But if we, most of the space is empty, so we end up having a lot of empty room between tokens that maybe it's possible though to discretize it into a nearest neighbor token, but it's kind of like much more, like it's much more like it's much less obvious why this would work. Sometimes when we go between tokens, it doesn't really make sense, and this is kind of a fundamentally hard problem in graph theory is actually the reality. Yes, this would work if your model's like perfect, and it would work if your model's perfect, but in practice, this is kind of like not the inductive bias we want to build into our model. It typically makes it pretty hard to like learn, for instance. So for something like, let's say, a diffusion model, there's like language diffusion models that like do this exact same procedure. You continuously embed your tokens. You take a diffusion process there. Like the issue that we'll see like for like those models that we've seen for those models is that they're not really competitive with like your standard autoregressive model, and they take way too long because you have to you can't have any error whatsoever. If you have any error whatsoever, you're just kind of lost. It doesn't work. For autoregressive modeling, we model the probabilities, which is a different quantity than modeling the actual value. So we can like model the probabilities of like, let's say the probability of the word the or versus the probability of the word times. And this is like a very continuous quantity. But if we were to say like, hey, let's just like take a transformer, we push it through a linear layer, and you select one value, right? This would be the setup. You would select one value from your like continuous space. Not like you don't have a probabilities for all the other tokens. You just select one value. This will become more difficult. We try to like generate like something that's in distribution, so something near one of these tokens. But yeah, this is the case. Yeah, basically we're modeling a probabilistic model. We try to discretize, and there's just a lot of empty space. This is not a good inductive bias to learn over. And so because of these various issues, we only have like one really good like discrete probabilistic model. You notice as the autoregressive model, it's transformers. This is very, very typical. The idea here is that the idea here is you model the probability of each of your sequences X by decomposing it by token. So you model the first token here, and then you take the second token given the first token, that's the next probability, and you just multiply it out to get like the probability of the last token given every token beforehand, which is your typical setup. And yeah, and for language in particular, this decomposes as the idea of context in green. So you have a context value, a context tokens, and you have a next word prediction in purple, basically. And this is the reason why this works so well. And yeah, there's several good upsides to this autoregressive modeling paradigm. So in particular, it's very scalable. The idea here is that when you compute like each next token probability, you only need to compute a probability over your D total tokens, right? Or your N total values. And this is like very scalable. This like, it's very easy to do this as long as you can like build your architecture sufficiently good. This should work out pretty well. Another thing is that if you have a very strong neural network, if you have a neural network that is sufficiently powerful, then you can theoretically represent any probability over your sequences by this like decomposition, which is counterintuitive, but it actually works itself out due to this decomposition nature. And finally, it's actually a pretty reasonable inductive bias for stuff like natural language. So for natural language, we speak, we write from left to right. So it's pretty natural that we would do so here for like modeling language, like for modeling language, this will make sense as well. There are several downsides, though, which have been largely unaddressed by most people because of this over-reliance on autoregressive modeling. One famous argument that people like Jan LeCun have really been proponents of is the idea that sampling and autoregressive modeling tends to drift. So when you sample from an autoregressive sequence, you just generate new tokens, but you can accumulate an error, and as you continuously accumulate the error, this will cause your generation to veer off course. This is a very famous argument for why we're not going to get AGI through autoregressive modeling. And another issue is that for non-language tasks, like let's say DNA sequence, well, there's DNA sequencing. There's no reason why DNA sequences have to be generated from left to right. I mean, this is not very. This doesn't make sense as an inductive bias. Furthermore, and this is something that people haven't really been thinking of, but actually when we have an autoregressive transformer, there's actually a lot of constraints that we need to place on our autoregressive transformer. In particular, making sure that the attention mask is causal, that people haven't really been cognizant of, but there are definitely still problems for this probabilistic modeling paradigm. And finally, because we sample iteratively in autoregressive models, we generate next tokens. This is actually a pretty slow technique because of the fact that it's rather iterative. You have to generate tokens one at a time, which is not great. So yeah, we have all these problems and benefits of autoregressive modeling. So the question that we need to ask ourselves is there something more to this? And we can think about it in terms of score matching, which I'm sure you're all aware of. And yeah, the key idea behind why we can't just model p theta of x directly, instead of why we have to do this autoregressive decomposition, is because p theta of x, we have to make sure that as we sum over all the different sequences, we have to sum up to be 1. And this is impossible because there's an exponential number of sequences that we need to sum over. And so this is very similar to this idea of score matching that we've just been talking about for the last couple of lectures, where we model this gradient log probability function. And when we do that, we don't have to we don't have to sum up over all the possible numbers. We don't have to integrate out the distribution to be 1, which tends to work pretty well with when you combine it with stuff like diffusion models. So the real question here, and the thing that we'll talk about for the rest of the lecture, is how we can generalize these techniques from score matching to our more discrete case. And that is the real question of this lecture. Can we do it, and how well does it work? So let's take a look at the outline of how we can get about doing this. There's 3 steps. The first is how do we extend score matching to discrete spaces. This is not a very well-known. This is a pretty well-known problem, and there haven't been really many good solutions that have been proposed previously. The next question is that once we learn the score, which in the discrete case is called the concrete score, how do we generate new samples using concrete scores? And finally, when we build this generative model to generate new sequences, can we evaluate likelihoods? And the reason why we want to evaluate likelihoods is to compare fairly with autoregressive modeling on a lot of perplexity-like tasks. And so yeah, first point, can we look at generalizing score matching to discrete spaces? So when we think about the core building block of the score matching, we really think about the gradient, and the gradient actually has a nice way we can build it. There's a nice generalization of the gradient to a discrete space. So the idea here is our gradient of a function of f, when we evaluate at a position x, this is actually a finite difference, because a finite difference is the generalization of a derivative if we assume that the space is not continuous. So yeah, so this gradient becomes fy minus fx when we just index over all other y's. And this is like the generalization of a gradient. And using this, we can build a generalization of a score function. So the score function is a gradient at a position x of log probability. And really what this is a gradient of the probability over the probability when we like do chain rule to get out the logarithm. And then when we substitute our definition of our finite difference instead of the gradient in this second line there, what we actually get is that this is the collection of all py over px minus 1. So this py over px indexed over all y. This is what we'll learn. This is called the concrete score. And this directly generalizes the score function from continuous space to discrete space, which is nice. But how do we learn this? Okay, there's one thing, which is that for py over px, when we try to model all py's over px's, this doesn't make a lot of sense computationally. So in this case, for y, if we just let y be any other neighbor of x, any other value that's not x, then we end up with this issue where we have to model too many quantities. O of n to the power of 2d exponential doesn't work. But instead, if we model these ratios, where we model the ratios between two sequences that differ by only one position. Okay, so instead, let's model the ratios between any two sequences that only differ at one point, or at one position, which is a much more local construction. And if we do this, this is only complexity of O of n times d. So this is very much more computationally feasible. This is only the size of our sequence. And when we model these ratios between two sequences that differ only at one position, we can actually parameterize. Okay, but we'll normally write it out with this first value, this py over px for all of our derivations. But all the derivations can generalize pretty easily to this multidimensional case here, just as a precursor for the rest of the talk. That's because it's simpler to write it out this way. But yeah. We can also model our these ratios pretty easily with a neural network. So if we feed into the neural network a sequence x1 to xd, we push it through a sequence neural network, and then we can get out another sequence with another dimension attached to it, as such, and we can have probability of 1 x2 all the way to xd over probability of x1 over xd, and we have these. We can directly model these ratios of all successive neighbors, which differ only at one point this way. Sequence to sequence. So you just go from this sequence, it's one-dimensional sequence to a d-dimensional sequence. So we just push it through a neural network in parallel. So you can think about it as a non-autoregressive BERT-style transformer. Okay, so yeah, this is the idea. We have a sequence-to-sequence model. We can generate the ratios of places that differ only at one position. So how do we learn it? As it's a very arduous question. How do we learn this concrete score? And how do we do this? So yeah, our goal here is to learn a neural network S theta x, such that when we parameterize S theta of x at a position y, then we can get the relative ratio py over px. And we need to find a way to do this in a very principled manner, as in we can't allow negative values for our S theta. And also, when we have enough data, we should also be able to recover a ground truth, or enough data, enough model capacity. And so the way that we do this is very similar to score matching, which is the following loss function. We're calling it score entropy because it's based off of it's very related to stuff like cross entropy. But I guess the idea here is that it's a discrete generalization of score matching in the sense that we take an integral over all x in our probability function p, and then we sum over all of our y that are neighbors, and then we minimize this type of new type of divergence function in the middle here in order to optimize it. And yeah, the reason why this is in such a way, we'll see it. We'll see why we need to do this type of construction soon. But the idea here is that we have the score entropy. It's a generalization of score matching, but for our discrete scores instead. And you might not believe me, but actually this score entropy function actually does recover our ground truth. So if we just get rid of all the x and y, if we simplify our notation a bit, and we want to minimize the following quantity. Well, this quantity is minimized when our derivative we just set the derivative to be 0, and we get this 1 minus py over px times 1 over s is equal to 0. and then we move it back over, we multiply it out, and we get that when we minimize it correctly, this S value should be equal to Py over Px. And we can also visualize the loss function for something like a ground truth ratio of 0.2. And we can clearly see that it satisfies all of our requirements. Basically, it's convex, and it will recover the true value if we just minimize this. And finally, we can do this for all pairs x and y. So we can just do this independently for all of our x and y, which means that if we learn everything correctly, we should recover the ground truth for every pair x and y, basically. So yeah, we have this score entropy loss function, and how do we actually optimize it? Very similarly to score matching, here's the issue, right? We have this loss function, but this Py over Px, this ground truth value, is not known to us at all. I mean, if we knew it, we could just use it. So it would make sense that we have to find a different way around this in order to learn it. And we have two different ways of doing this. One of these alternative loss functions, which we're calling implicit score entropy. This is a natural generalization of implicit score matching, but we won't be covering it in this lecture, but just nice to know that exists. And we also have another loss function called denoising score entropy, or denoising score entropy. And this is analogous to denoising score matching for our score entropy case. To look at denoising score entropy, here's the idea. If we assume that our Px is equal to a convolution between a base distribution P0 and some kernel P, well then we can write out our probability as this summation over all x0. And when we do that, we can take a look at our initial score entropy loss, and then yeah, the idea here is we can just remove the expectation as first. So instead of we just move in the Px, and that gets rid of the Px in the denominator, but the summation over all x. Then in order to look at things more concretely, we take a look at this decomposition above, and we just apply to this Py term to get out this following decomposition, which is basically we add in a expectation over x0. We can basically move around our values a bit, so we can move the summation term to the front by Fubini's theorem, and we can also add in a p of x given x0 given over p of x given x0. So we can kind of rework it here, and then once we have everything in this setup, then we can basically just take the last two terms into our expectation. We just move those terms, take them away from the summation, and move it into our expectation. And it just gives us an equivalent form. And the nice thing that we'll notice for this equivalent form here is that we only have this relative ratio of p of y given x0 over p of x given x0, not p of y over p of x. And as such, this is possible to compute. And this is something that's possible to compute because we can assume that our transition kernel P is tractable, but we can't assume that our data distribution P is tractable, basically. Okay, this x0 is kind of your base to data point, and this transition kernel, it can be anything, basically. It could be anything. So much more than just this type of noise. But in the continuous case, you would also write out this, but for practical reasons, that's why people choose to use a small Gaussian addition in order to do this same exact thing. But this is basically the same exact thing. So we have this way to get rid of the Py over Px. And yeah, as such, we have the following denoising score entropy loss function. And it's particularly scalable because we can sample in x0. We can sample through we can sample through the perturbation kernel. And then we only need to compute this s theta of x once for this summation value because we're only using s theta of x. And then finally, we can compute this ratio of transition kernels by just the way that we define it. So everything becomes computationally tractable, and we can optimize this loss. So now that we have a way of learning the concrete score, the next question is how can we sample using the concrete score? We have this way of estimating the concrete score, learning the ratio of the data distribution. How do we generate new samples? And this is really diffusion oriented. So in order to do this, we have to define a diffusion process for our discrete tokens, kind of. And as we all know, diffusion is just a probabilistic evolution, a way to go from P0 to some PT. So we can work off of this direction directly. Our PT now is just a big vector. We can think about it as a big vector. So it's because each of our probability at a certain sequence is basically just like some number that is greater or equal to 0, and everything sums up to be 1. So we can think about it as a big vector, kind of. And in the way that we evolve our distribution is with like an ordinary differential equation. This is the most natural way of doing things. So our PT is a vector. We take a time derivative with respect to that, and then we can compute the transition based off of this matrix QT times our initial vector PT. So we do a matrix vector multiplication. And some things about this diffusion matrix that are not obvious, but these are just hard requirements. We need to make sure that this diffusion matrix has columns which sum up to be 0. And also we need to make sure that this diffusion matrix is non-negative at all non-diagonal points, basically. And the idea here is that QT controls how often we jump from one state to another. And we can do this pretty directly here. So basically, if we want to jump from a state I to a state j over a period of delta t, then basically we just take a look at whether or not we stay at the current function, and then we just add the following matrix term times delta t, and then we have some second order term that we get rid of for practical purposes. This is kind of the analog of Euler-Maruyama sampling for diffusion models, this time discretization of our sampling process. And so we can clearly see here that our QT is, these matrix entries are the jump transition rates between I to j, kind of. Yeah. And so once we have this set up, let's take a look at a couple of examples. This is not a very intuitive thing. But let's take a look at the following QT. Our QT is given by this matrix, this -2, -2, -2 on a diagonal, one everywhere else matrix. And let's say we take an initial distribution of 0.5, 0.2, 0.3. When we multiply this stuff out, we get a transition rate of -0.5, 0.1, 0.4. And what's interesting about this is that the values sum up to be 0, which is important in order to maintain the fact that our probability always sums up to be 1. And also it's always a valid transition rate between different states. For this type of setup, we can actually compute the intermediate densities PT by just exponentiating out this matrix times this 0.5, 0.3, 0.2 initial vector, which allows us to compute intermediate densities by solving the ODE, basically. And if we do this, we can actually also check to make sure that the transition actually satisfies this above statement, basically. Well, for the first value, you're losing mass at a rate of -0.5, and then the other two are gaining mass at 0.1, 0.4. So the total mass remains the same, but the relative ratios change. Building off of that, basically, generally speaking, we'll take a QT is equal to a sigma noise level times a Q matrix. And then once we have that, this becomes a linear ODE. Everything linearizes, we have a linear ODE. And in order to solve basically just very general, we can solve the intermediate densities by solving this doing this matrix exponentiation in order to solve the linear ODE. Basically here, there are many ways to compute this exponentiation, but simpler is better. And the idea here is that we can calculate the transition rates with a long horizon transition rates through this by taking column and by taking entries of our exponentiated matrix, basically. So yeah, this is great. And another thing that's also important for diffusion is that as t goes to infinity, our PT will go to a p base, basically. So this is just making sure that we approach a nice base distribution, basically. I guess the other thing to, in this case, we can take a look at the following matrix, this -2 matrix. We exponentiate out with respect to some t, and we get this thing, basically. It's not as bad as it looks. And then as we go to infinite time, we just go to a random value, basically. So this is a uniform transition matrix. We just go from initial point to any other point randomly, eventually. Similarly, we have this masking thing where we add a new dimension. We add a new dimension to our three-dimensional case. And basically, we only have transitions to this new state. And our exponentiated matrix looks like this. And as we take infinite time, the diagonal disappears, and everything goes to mask, basically. This is a masked transition. Well, in the first case, basically the idea here is you just randomly go from like your initial like value to any other random value. And the second case is like you randomly go from your initial value to like a mask value, basically. Just so like it just determines like where you're moving, kind of. We have this continuous time Markov chain setup, and generally, when we're looking at sequences, the idea here is instead of perturbing from sequence to sequence, which would be like very expensive because then we have to consider the transitions between in our sequence or any other sequence. And this is computationally intractable. We instead like go from token to token. So instead we just flip one token at a time, kind of would be the idea. And as such, this is O of d squared because we only have to consider one token. And because of this, when we do our overall transition between sequences, it just becomes overall transitions between tokens. So it factorizes, basically. This is just like another point there. And what's nice about this is that we can chain this with our score entropy to estimate like the intermediate like density ratios. So if we assume that our samples are from, assume we have some samples x0 given from p0, then we can learn our s theta. We now add a t value in order to estimate the pt over pt values, pt ratios. So we have another extra t input, but it's the same setup. And then we have our denoising like score entropy loss function. And the idea here is like, now we can take these transition values. This just transition between two different states. This is all given by our initial rate matrix Q, basically. So more or less what this is saying is that we can like optimize our denoising score entropy using this like Q setup, using this diffusion setup. It's all very natural. And so the question here is that, okay, now we have a way of like, going from data to noise. We also have a way of like estimating the intermediate ratios. What can we do with this? Well, the idea here is we can reverse the diffusion process. So if we go from P0 to PT, which is P data to P base, roughly speaking, the idea here is can we go back from P base back to P data? And actually, there is a way of doing this. So there is this other type of diffusion, like reverse diffusion process, where basically we take the time derivative, but in here, we're going backwards in time, and we have a new matrix Q bar, which is like a bit more different. And the idea behind Q bar is that Q bar is like, for an input j and I, this is equal to like the density ratio pt of j over pt of I, and times this initial qt ij, for any I and j not equal. Basically, we have this following relationship between the forward and reverse diffusion matrices, which is pretty neat. And also, I guess the other thing to note here, I won't write it out, is that for qt I of I, or bar qt I of I, I'm not going to write that out because you just need to make sure the column sum to 0. So we assume it's just we can extract it from the other values, basically. It's I and j represents like an index, basically. So like, for our purposes, it'll be like a sequence, but this is like kind of hard to write out. But you can think about it like in matrix, you just take a matrix and vector. So the matrix, you just take the the j row ith column entry, and then you take the ratio between the two corresponding entries in the vector, which is the probability vector. But yeah. So yeah, we have this reverse setup, and again, what's nice is that we had this appearance of our ratio, basically, of our concrete score. So in particular, we can approximate it with our learned concrete score function, our score network S theta. And this is kind of goes back to the reason why we parameterize everything this way, is that the way that we do it is that we have initial state I, and then we basically compute the concrete score of S theta IT, and this goes over all the various J indices. And if we do this, it allows us to in parallel jump to any of the other states that we want to jump in because of the way that we parameterize things. So everything kind of works its way together in this setup. As an example, we can have this initial matrix here. We multiply it out. This is the rate, -0.5, 0.1, 0.4. And then we can construct the corresponding reverse matrix here. This reverse matrix, if you work itself out, it looks something like this, basically, where we add in the ratios of the data value at the data vector at the time. And then we multiply this reverse matrix by this probability vector. And actually, what you'll get out is the exact reverse. It's the exact reverse, the 0.5, -0.1, -0.4. So here we can see that it works, basically. And as an example, we also we can visualize it as follows between the uniform, where it basically just goes to other random values, and eventually it denoises to some initial sequence. And also we have it for the mask, basically, where we can go from mask to our initial tokens. So this is all pretty nice. We have this nice setup. And well, there's only one other problem that we kind of have, which is basically when we try to actually do this reverse sampling, when we try to go through the various when we try to simulate the reverse, it's pretty slow. The reason why it's so slow is because we are jumping from this all fundamentally comes down to our computational consideration. Basically, our x1 to xd, we're only jumping between that and another sequence, which only differs at one point or at one position. And so, when we construct a reverse, we can only also jump between sequences that are different, but only by one position, which you can imagine would be very expensive, especially if you need to jump, if you need to continuously refine the individual positions simultaneously, as such. And so we cheat, basically. That's how we sample. We basically allow multiple steps within we allow one to sample multiple jumps in one sample step, basically. So instead of going individually unmasking the tokens, let's say it was the mask of mask, we just unmask both of these tokens simultaneously. We can do this pretty easily given our setup, but it's more or less kind of a way. There's a way we can do this, and we can just do instead of sample to it was the best of times in one step, allowing us to go through two different jumps at once. So yeah, we can put everything together. We have the entire setup built. So the first idea is that we get some samples from our desired data distribution that we want to model. We define a forward diffusion process, whether it be the uniform or the mask or whatever, or maybe something more exotic. These forward diffusion process given the transitions. And then we can learn the ratios using our score entropy loss function that we've defined. And then we can use these ratios to reverse the diffusion process, including adding in some discretization to make sampling faster. And let's see how this works. So this is an example of a text sequence that we were able to generate just randomly from our corpus. This is a GPT-2 level sampling procedure, or GPT-2 level data set and model size. And yeah, it's reasonably coherent, and everything. It's it works, kind of. That's kind of the idea, it works. But the idea here is how does it compare with autoregressive modeling on the scale of data set? So we can compare samples as such, and we have a GPT-2. We're calling our model score entropy discrete diffusion, so SEDD, SED. And so we have the GPT-2 model on the top. We have a SED model with an absorbing transition, which is kind of you go to the mask token. And we have a SED with a uniform transition, SED-U, which means that you go from your token to another random token whenever you transition. And generally, we're able to see that our SEDD SED models tend to outperform GPT-2 in terms of coherence when we do this baseline sampling method, when we try to sample from the distribution. And we can also visualize this more as a function of number of sampling steps versus quality. So in this graph on the right here, we have our two GPT-2 models. If we try to generate out long sequences, it tends to look like something like this, where we generate out it takes 1024 network evaluation functional evaluations in order to generate one of these outputs. And yeah, it tends to be pretty high. When we feed in these generated sequences into another model, another larger model, they tend to say, hey, these sequences are very high perplexity. These sequences are kind of very low likelihood. These sequences don't make sense, basically. So we can see here that GPT-2 tends it tends to be pretty bad in terms of our evaluation as such, even from both the small and the medium. But these lines, which are our SED models, basically, we can kind of trade off the compute versus the number of we can try to trade off quality and compute, basically. So if we only take 64 steps, which means that we're doing a lot of discretization, we take a lot of simultaneous jumps, we end up with this kind of model that kind of matches GPT-2 in terms of its generated quality, but it's much faster, basically. And also, if we really crank up the number of iteration steps, so we take let's say 1024 or even 2048 sampling discretization steps, what we see here is that our quality gets progressively better and better in a log log linear type of fashion. So basically, we're able to generate sequences that are just significantly lower in terms of generative perplexity, which means that they're much better sequences if we just crank up a number of steps. We can't do it with GPT-3 or GPT-4, mostly because of model size. These in this case, our model sizes are pretty small, 100 million parameters, 400 million parameters. So we're matching the models by color. So blue models are small, orange models are medium. For GPT-3 and GPT-4, the other issue is that data set is private, basically. But for our GPT-2, the data set is web text or open web text, which is why we can kind of do an apples-to-apples comparison. Yeah. But yeah, so the conclusion here is that, so quite surprisingly and pretty nice, and this is a pretty strong motivating factor, is that this discrete diffusion model with score entropy tends to outperform autoregressive transformers, at least for generation quality and speed. And I guess another interesting thing, and this is another important thing, is that for this type of generative modeling technique, what we need to do is we need to have controllable generation. We need to be able to control how we generate. And at least in this case, we can do something similar. We can do prompting, but the new and interesting thing is that we can prompt from an arbitrary location. So if we have this top one here, we can take our blue prompt text, and the idea here is that when we generate our new sequence, we just generate around it. We don't change the prompt text, but we just generate everything else around it. This actually is principled if you go through the math, and it allows you to fill in the rest of the information there. So we can also have something in the middle where we have these two prompt tokens, sequences of prompt tokens in the middle. We just generate around it, and this allows us to infill. And it typically tends to produce pretty coherent statements, basically, which means that we're able to control the generation process in a new, more interesting way, kind of. And which is this is not you can't do this with a typical autoregressive model. So now that we have our generation quality, the last thing that we need to look at is how do we actually evaluate likelihoods of this generative process. So we've shown how we can learn, we've shown how we can generate, how can we evaluate for likelihoods? So the typical metric that people use for evaluating likelihoods is perplexity. The perplexity of an input sequence, x, is basically just this e to the power of -1/d times the log probability of x1 to xd. So this is a very typical metric for use for autoregressive modeling. The reason why is because it's a relatively principled way of measuring the model ability. So if we can have a very low perplexity on some other data set, it means that we're generalizing pretty well. We're compressing things, which is typically a good sign. Also, we can directly compare. This is directly computable for autoregressive modeling because we can compute this p theta directly. And finally, we also tend to optimize with respect to something like this because at least for autoregressive modeling, we optimize with respect to this negative log probability and just taking an exponential or effectively optimizing this something similar, so which is why we can report something like this, basically. Yeah, and so for diffusion models, long story short, we can also do something similar. The math actually tends to be kind of a bit involved, but the key insight here is that we can take this under some mild conditions, some very mild conditions on our base distribution, how long we diffuse for, our generative process has the following likelihood bound, basically. So our negative log likelihood is bounded above by this integral and with this expected value and all this stuff. And when we also add some known constant c. The c constant is known a priori. And what's interesting here is that this integral and whatnot, this is exactly our score, the denoising score entropy loss, if we recall back to a couple of slides ago. And yeah, the only new thing is that we have to weight it by this qt of xty, which is kind of this other weighting. It doesn't really affect anything in for any of the computations, basically. It's just kind of this other weighting. But yeah, we can just, which means we can basically train with respect to this loss, this upper, this log likelihood bound loss. And so yeah, we end up getting a perplexity bound because we can just take the perplexity of the input sequence, we just feed it through this denoising score entropy loss with this weighting, and yeah, we basically get an upper bound just by the fact that things are the E is monotonic basically, which allows us to report perplexity values as well. How does it work in practice? Well, across all these like different models, we like do this whole GPT-2 like train on open web text, evaluate on other types of data sets type of setup. And yeah, what we see here like pretty consistently is that like our GPT-2 model, it does tend to produce the best likelihood values, but SEDD like with absorbing masking transition, it tends to like be like very close basically. So for most of these like data sets, if we have a pretty close value within plus 10% or so, we underline it. And the reason why we have this plus 10% like cutoff is because of the fact that we're only reporting a bound and not the true like ground truth like non-bound likelihood perplexity. But yeah, we have this like underline here, and we also have the best results bolded. And what we consistently see is that our SED model, it can like basically match on like Wikitext 2, Wikitext 103. It has to fall within this perplexity bound. And for something like PTB, it actually outperforms like the existing model, like an existing GPT-2 like pre-trained model, and sometimes by a pretty considerable margin, as shown in like this middle bar here, basically this middle line here. And yeah, so this is great because now we can show that basically we can challenge autoregressive modeling not only on like generation quality, which is a bit more like of a there's more moving parts there, but also on perplexity, which is a more like streamlined, more like compact way of like of comparing between two different autoregressive models. Well, what you would do here is you would just like generate up to like a end of text token, and you just like post-process it kind of. And typically for like this open web text data, like sequences are pretty long, like 700 or so tokens out of the 1024. So it's like pretty comparable, basically. Yeah. But yeah, okay, yeah, just to summarize. Yeah, so first thing is that, yeah, it's pretty hard to build probabilistic models for discrete spaces. We have like GANs, VAEs, like diffusion models. A lot of these things are pretty hard to like naively extend from like continuous space to discrete space, which is why we only really have autoregressive modeling as a way of doing things. Yeah, basically, so yeah, autoregressive modeling is the only like really viable paradigm in this like space. The idea here is that we can extend score-based models to discrete spaces. And we can do this by, instead of modeling the gradients of the data distribution, we model the ratios of the data distribution, also known as a concrete score. We optimize this new score matching loss called score entropy, which we can also have these denoising and implicit variants of, which make it tractable. And then we can sample from our like process. We can sample from our score-based model using a diffusion process, using a forward and reverse diffusion process. So in particular, the forward diffusion process synergizes with our denoising score entropy loss, which makes everything pretty seamless to integrate together. And we can make it fast and controllable for our generation, which is nice. And finally, our generation quality can surpass autoregressive modeling because of the fact that we don't have to worry about like context. We can just generate the whole sequence in parallel, and this allows us more information during the generation process. Finally, we also have a likelihood bound based off of score entropy. This basically lines up perfectly with like our score entropy loss basically lines up perfectly with the likelihood bound that one would hope to like optimize or compare with. And for this like task, we basically challenge autoregressive dominance for the first time on like any large enough like sequence, like a GPT-2 level like result. Yeah, for this case, we're computing a bound on the negative log likelihood, and then the negative log likelihood, it goes into the perplexity here. So perplexity will kind of be like a forward KL divergence, and this is like a reverse KL divergence will be the way that this is modeled. So basically, yeah, so GPT-2, like, if we like remove the fact that we're only reporting a bound, it tends to outperform, but really it's much closer than that. But like, which means that it's covering the modes of the data distribution like sufficiently well. But like if it also has like leakage, basically, we can generate sequences that are low probability, but like this doesn't show up in our KL divergence loss. So previously you had like this embedded into continuous space. Generally, the issue that people have found is that like it doesn't really work as well. Like the log likelihoods like are, so we typically like, let's take a look at this like graph, this thing here. So like for previous like continuous diffusion models, it'd be like way worse basically. like much worse, like 2.5 times worse, something like this. Like this is typically like the range for like this continuous to discrete diffusion model where we like discretize the tokens. And also the issue is that for generation quality, it's like much slower. Basically, when we try to like generate the sequences, it becomes like, yeah, because it's like so sparse, we have to like make sure we don't have much error. So we have to like take a lot of discretization steps. So for example, like for some models, we'd have to take like 4,000 steps in order to generate a 1,000 length sequence, which is just too much, basically. The idea is that hopefully the error isn't that much, and you can jump between the two. There's some principled way of doing it, and it shows it's called tau leaping. If you're familiar with the it's called tau leaping in the chemical like engineering literature or whatever, and it kind of works. So if you take like very small steps, it will like it's going to be like reasonably conditionally independent, assuming like your ratios don't change too much, like your model doesn't change too much. So it's kind of like it's a discretization scheme basically. So like diffusion models, we also have a similar discretization scheme in Euler-Mari. Presumably, you can learn any like probability distribution over your discrete space with both methods. Yeah, but the question here is about which one builds in a better inductive bias and is more amenable for optimization. Qt is kind of like the transition rate, but we like exponentiate it. So like in particular, we have this. So basically, the Qt is a transition rate, and this exponentiated matrix is a transition kernel. We can do it for like many time steps, but like the issue here is that it's better to like put in a time step, so it becomes like easier. Basically, the fundamental Q tends to like stay the same, but we just multiply it by some noise level. So it's like kind of like all built in. Q is just a transition rate, so like something like this basically. It would go from like uniformly. This is how we go to other things uniformly, kind of. Or like in this case where we go to a mask token. So at each time step, like the Q basically is like scaled effectively. So we have a scaling to how much noise we add in at each time step. Yeah, the scale is controlled by the sigma. So this bound is basically an elbow bound basically from a VAE. So you would assume that your diffusion model, you have your forward diffusion process, which is your like encoding layer in your VAE, and this is your reverse, and you're learning the reverse diffusion process, which is your decoder. And then if you just work that out, you plug it in, you get this. This is the elbow that you get out, basically. Yeah, it's this architecture right here is the key idea here. And the sequence neural network is just like a transformer. We just basically make a transformer, but we have like a non-causal mask, so which allows us to go like, which allows the attention layer to like go from to be like completely like from everything to everything, basically. So it's like BERT, basically. Yeah, it would be like this. For question answering, it would be like this, basically. You just like fill it in. You fill it in. Yeah, we have like we're separating out between like the GPT-2 the small models and the medium models, and between like the medium models, we have the absorbing and uniform state, basically. So we have this like uniform transition matrix and or this masking transition matrix, basically. And typically, we see that the uniform tends to produce like worse results in the masking, basically. So like just randomly like flipping words, and this makes sense because if you randomly flip words, then you're going to end up with like sequences that like kind of don't make sense. Whereas if you just mask the word, then the sequences still make sense broadly. I mean, if you assume that we can like fill in the masks. In this case, this is a generative perplexity, which is basically we generate a new sequence, and then we take like a GPT-2 large model, and we evaluate the perplexity of this generated sequence on our GPT-2 large. And it's a pretty common evaluation to use like GPT-2 large to evaluate the things. There's a bunch of different metrics that are built off of this. We also took a look at like a Frechet distance metric, and it's also like it also tends to work, like see an improvement there, basically. So basically, yeah, you could take like a larger model and then like try to like extract some feature representations or some values in order to view your smaller model outputs. Yeah. Like the issue here is that we need to compute this exponential quickly, and if our Q is, let's say, like a GPT-2 like tokenizer size, the total number of tokens is like 50,000, right? Well, if we want to compute this matrix exponential, it's like it takes way too long. Like it will take like 10 seconds just to compute this or whatever, even on CUDA, or even on GPU, because of like how massive it is. We tried experimenting with like other like more like complex Q. that would allow us to do this computation easier, but it just doesn't tend to work because of the fact that it is kind of a fundamentally different architectural design choice, basically. It's not built for CUDA to do this matrix exponential. Thanks everyone for attending. Thanks everyone for listening. I hope you learned something.